I have to share my screen. Okay, so let's continue with this lesson. This is, I mean, this part is the second part of the lesson that we started the other day. We closed more or less here in this part about construction tools, and this is an overview of some tools and some techniques that you can do to do software. Okay, so this is an overview of the tools that a software architect can choose. Here, I mean, we could talk a lot about this kind of construction tools, but we are not going to do that because, I mean, some of those tools you already know, and other tools probably you will know in other courses later, and some of those tools are just depending on the technology that you are using. But I think it's important that at least you have some kind of classification on the main kind of tools that you can use. The first kind of tools that you can use in your software projects, is, of course, are languages, programming languages, because at the end, the idea of a programming language is that you have to communicate to the computer what you want the computer to do. Okay, so that's the main idea. We already said something about this the other day. So you have configuration languages. In principle, those languages have the feature that they are declarative because you don't want to have a full programming language to do some kind of configuration. So you have usually XML, JSON. I put here Turtle because in Solid they use Turtle files inside Solid. Turtle is it's similar to, is this based on RDF? It's an RDF syntax, but in principle, there is a syntax for Turtle which is called JSON-LD, which is based on JSON. So if you know JSON, probably you could work with a syntax version of Turtle, which is JSON-LD, and you can convert from Turtle to JSON-LD. Okay. There are other languages, for example, scripting languages. You already know about shell scripts, and they are also used a lot in a lot of projects. So usually for some things that are necessary to configure the system and so on. And finally, there's also the biggest, the most common tool that most of the software projects have they are developed in some kind of programming language. Here again, you have lots of different programming languages, high level, low level, etc. I put here just Java, JavaScript, but of course there are thousands of programming languages. There are other types of languages, for example, visual languages that, for example, if you know about the Scratch for children, is also a kind of visual languages. And there was a trend some time ago that was trying to suggest people to use visual languages, but at the end, it didn't succeed. So, I'm not sure if I think with nice tools and nice integrated development environments, it's usually easier to use programming languages where you have text-based programming language than a visual language. But again, these trends usually change, so maybe in the future you will use a visual language. And there are also what are called formal languages, which are based on logic, and you have for example, in UML, you have OCL, the set language, etc. About coding and programming languages and coding, there are a lot of things that we could say. This part is probably part of other kind of courses. It's usually very, very important to have a good naming conventions and to follow the naming convention of the programming language that you choose. It's not the same if you are programming in Python than if you are programming in Java or in JavaScript. So probably the naming conventions are different. And this is important that you try to follow those kind of naming conventions. Also the same for error handling. If you are using, for example, asynchronous code in JavaScript, there is a convention that the callback, the first argument of the callback is the error, and this kind of thing. So usually you have to, it's very important that you all understand what are the naming conventions and the conventions, the best practices of the programming languages that you are using. It's the same can be said about the source code, how to organize the source code. for example, in React, that you are using this year React for the lab assignment, well, you can choose to use React. In React, for example, it is usually very liberal on how you organize the project in different folders. So you can choose more or less the structure that you want. That's different, for example, if you are using Java. In Java, especially in Maven projects, you have a folder for the source, another folder for the test, and so on. So those kind of conventions usually change depending on the technology that you are using. And then there is this code documentation. I think it's really important that you try to, I mean, the more documentation that you can create automatically in a light way, usually the better, because then you are not going to be very worried about how to maintain that documentation. Okay. And as I said here about the code documentation, I already said that the other day, it's also important not for you, not for the computer, but for other programmers and other maintainers, because most of the projects at the end, there will be other people who are going to use your project. Of course, about testing, we could say a lot of things about testing, and there is some kind of best practices to separate the test code and the dependencies from the test code from the production code, especially in Java. But for example, in React, they don't do the same. They put the test code. They usually, I mean, depends on the people, but in some projects they put the test code in the same folder as the production code. So it depends on what system you are using. It's very important that you construct your software so it could be later reused, because maintaining the software is usually a very important aspect. So you can, for example, add parameters to your system. So, for example, if you have a system that depends on some magical numbers, try to avoid the magical numbers in the code, and you can put them in a different system. For example, in a resources file. So those kind of things are usually very good. So you can later reuse that code for a different purpose. Okay. You can also have conditional compilation, encapsulation. We are going to talk more about this later about modules, and you also can have this kind of packaging. And here I said this is a very common mistake, is that people usually do a lot of things automatically, but when they have to package their system, they let that part to do it manually. And that's usually something that is an anti-pattern. An anti-pattern is to do tasks that could be automated to do them by hand or manually. That's usually not a good. That's usually a mistake. And of course, you have to do documentation about the API, etc. And also construction with reuse. So you also have to build software that you are reusing other parts or other software. We will later have a specific section about dependencies, because at the end your software will depend on other software. Nowadays, I mean, it's almost impossible that you will have to develop some software and that software doesn't depend on other things. So this is something that has been changing in the last 23 and 30 years. Nowadays, you have a lot of software already, and you will depend on that software. Okay, so if you depend on external software, that external software can be updated. And then what happens? How do you handle the updates of that external software in your software? And that's usually another difficulty that you will have in your project, that you depend on libraries that are very frequently updated, then you have to automatically update your software, and that's usually some problem. And of course, you also have the legal issues about the licenses and so on. About the tools that you can choose to construct your software, of course, again, here you have a lot of choices. You have text editors. You have from VI, for Emacs, Visual Studio Code, Sublime. You also have integrated development environments. Nowadays, these text editors are evolving to behave almost as integrated development environments, I have to say at this moment, most of the time I use Visual Studio Code because I find it quite light and quite well. In other parts of my life, I was using Emacs, and I have to say that usually Emacs and the users of Emacs are very, very productive, much more than if you depend, for example, in Eclipse or IntelliJ, but also it depends on the kind of programming language that you are using. For example, if you are programming in Java, then usually these integrated development environments facilitate your life more than if you're programming in other languages. So it depends. Of course, this is a matter of choice. Some message I can tell you is that it is very important it's very important to master the construction tools that you are using. So if you are using a good construction tool, for example, Visual Studio Code, and you master it, for example, you can do some macros to automate some things, you will appreciate that later. So the best that you can manage your construction tool, you can master that, the better for you. Okay. Of course, there are also graphical user interfaces, and here I'm not. I don't like those very much, but they exist. And of course, you also have tools for quality assurance. And those are the tools that we are going to say now. Quality assurance are tools, for example, to help you with testing. So you have also test frameworks, you have also test coverage tools, and here, so this slide is mostly to tell you that, for example, we are using CodeCov in this year because this is a test coverage tool. So I expect you to know what is a test coverage system. Okay, so is that something that when you run the test, it just check what are the lines of code that have been run during the test. You also can have some tools to create assertions in your code, some preconditions that you put on your methods to be verified before running those methods. And you also have tools to do inspections and code reviews. And here one example is GitHub and the pull request with GitHub, which is a very interesting tool. And about code analysis tools, let's go to the next slide. Code analysis tools depend if they are a static code analysis or dynamic code analysis. Static are things that you can check about your code without running the code. So, for example, a good example here for you is Codasy. Codasy is an example of a tool that without running the code, it can check if there are some problems with the naming convention, some problems with the complexity of the code, and so on. But it doesn't need to run the code. Okay, and those are different from dynamic code analysis tools that they run the code, and once they have run the code, they give you some reports about for example, the profilers. They usually tell you how much CPU, memory, or method calls have been run or have been needed when you were running the code. Okay, and also test coverage tools. They usually need that. Probably they don't need that you run the code in production, but you run the code in testing, in the testing stage. Okay, and there is another tool which is program slicing. And this is nice, but I'm not going to tell you a lot of details about this because I found it's not very popular. But what they do is they run the program, and once they run the program, they tell you which parts of the program have been, what was the fragment of the program that has been run. Okay, so they were a bit popular some time ago. Nowadays, they are not so much popular, but maybe in the future there you will have some tools that allow to do this kind of program slicing. And these tools, for example, can optimize the code. For example, if you let a library, for example, to be run in production, and you later want to see what are the parts that you really need, then you can remove the other parts and have a subset of that language that really works for your use case. Okay. The other part, the other kind of systems that we are going to tell in this course are control version systems. And here, I mean, in this course, one nice thing is that nowadays most of you in the labs, you have been introduced to control version systems. So in these slides, I'm going to do it very fast, only to do some definitions that you know that, for example, in the exam, I can ask you about those definitions. So the definitions are: what is a repository? I think you already have this, where you store the changes of your system. What is the baseline? Baseline is usually the initial version. So you have a code system, software, some kind of software, and you create the baseline, which is the initial version. And from that version, you start doing some releases and snapshots. I usually I usually call them snapshots. And those snapshots, you can put them in the trunk, which is usually the trunk of the development. So, for example, here from this baseline, you are continually creating new releases, new versions. I have to say, versions are internal and releases are public. Okay, and then you also have the possibility to have a branch where you do some changes, and then later you can merge those changes back. And finally, you can also create some tags. So you say, okay, this tag is T1 and this one is T2, and maybe because I want later to do them publicly. Okay, so those are some common definitions. Other definitions is the possibility to do a checkout is that you have a local copy of one of those snapshots, and this is very, very important in Git, is that the command checkout allows you to go to, as I usually say, is that allows you to travel back in time. So you can go back to one local copy of those snapshots and recover something. So when you get used to work with these control version systems, you are not so much worried about losing some files or whatever, because you can go back in time and recover them. Okay, so a commit is when you create one of those snapshots. Merge is when you merge some set of changes. And now, I mean, later I will talk about a bit about branching styles. Version control. There are also two main types of version control systems. The first, the most popular, or the original, more popular, were centralized, but after Git, which was decentralized, was distributed, nowadays the most popular one is Git. But I think it's important that you know that, because there are some code which still are using Mercurial or Subversion, that you at least know that there are these CVS and Subversion. They were centralized. It meant that there was a central repository, and you always had to do commits to that central repository. But in Git, you have, for example, if you are using GitHub, you can have that central repository, but you can also use Git in your local machine, and you commit only to your local machine. So that's why it is distributed, because you have, if you have members of the team are distributed, and every member of the team can have its own copy of the Git control version system, and he can commit to that local copy. Okay. About Git, as I said, is very, very popular nowadays. I think it's probably it's like is the main one nowadays, and a lot of companies are just moving to use Git. But I have to say that it is not the only one. It was designed by Linus Torvalds, the author of Linux, in 2005, because he was not very happy with other controversial systems. The idea is that it can work with very large number of source code files, so it is very efficient. So this is a quality attribute. It allows to work in a distributed way, and also supports branching, non-linear development. So this is usually very important. I mean, some definitions about Git is that, I mean, you start with a local working copy in your laptop. So this is in your laptop, you have the local working copy. But you also have what is called the stage area. The stage area is, I mean, there are different names. It's also usually called the cache or the index, and this is like also in your machine. So in your machine, you have this possibility to have the stage area, and this is I usually like the metaphor that this is like the snapshot of the local working directory. So you take a snapshot, you can add things or remove things from that snapshot, and this is this rounded this circle is one of those snapshots, and then those snapshots you can commit then, and if you commit those snapshots, you're adding them to the control version system. So this is the control version system is when you put each of these snapshots. Okay, the latest one, the most recent one, is called head. So this is the head of your Git repository of your Git is the latest snapshot. That's why I put this in this way, because if you create a new one, you will create here on the bottom, and you will have a new head. So you will move this head here. Okay. What else? You can also work with Git with remote repositories. Usually when you connect with a remote repository, and this is what you usually do with GitHub, the first remote repository is usually called origin, and this is the initial remote repository. And then the workflow is the following. You can, in your local machine, you have the stage area, you have the local working directory, you have also the history of the commits, and with the latest one is the head, so you have this part. So, and you can move in this way. So if you say git add, you create the snapshot, git rm, you can remove from the snapshot, commit, you are adding to in your local machine, but all of this is in your local machine. And once you push or the other commands, clone, fetch, or pull, if you push, you are adding this to the remote repository. In this case, in your case, is GitHub, and you can also fetch or pull, or the first time you can clone. Okay, so these are the common actions that you can use in Git. Okay, probably you already know that, but this is just an overview. About branching, I think this is just a repeated slide, so these are the same definitions as before. But this is a new slide for this year, but I'm not only going to say that this is something that next Friday, some of the teams are going to talk more about this, which are called branching patterns. And there are at least three known branching patterns. I have to say that this Git flow and GitHub flow, a lot of people confuse them. So, and I was the first one that, I usually thought that they were the same because the names are very similar, but they are not exactly the same. And the difference is that in the Git flow, is this one where you have a develop branch, and then you also have other feature branches, and then also you can have some hotfix, and then you later have the master, which is the public one. In the GitHub, they usually say that you don't need to have, for example, the hotfix, and the develop usually is the same as the master. So they have some differences, and they promote pull requests. And finally, the trunk-based development, I have to say that at this moment is the one that I usually do in my projects, is that you don't have so much complicated things, and you work most of the time in the master, in the trunk, and sometimes you have some feature branching, but very short-lived, so very, very short ones. Okay, so and this is the one that I use in my projects. There is another topic about how to construct your software, and as I said before, is when you when your software depend on other libraries. What you can do with when you depend on other libraries. I have to say that this is not an easy topic, and this is something that usually, when you work, especially when you depend, when you are starting to work, you usually add most of the libraries that you need just on demand. When you need something, you create a new dependency. You put that in, for example, with Node, you create npm install whatever, and you put that in your project. And sometimes you didn't care so much about the license of that library, or also what is the stability of that library, because maybe that library was developed by some developer in some corner of the world, that developer is no longer maintaining that library, and later when you need something that library doesn't support you, or even you detect a bug and the bug is in that library, you have a problem. So sometimes it's very easy to just put npm install whatever library, but I mean, with experience, I can tell you that that usually is a problem. So be careful with the dependencies, and usually try to have some kind of justification of what libraries you are going to use. And there is something called the dependency graph, where you put the dependency graph is when you say that you have one module depends on another module, and this module depends on another module, and so on. The problem sometimes is, I will tell you later, is that you may have some circularities in those dependencies, and that usually is a problem. And the problem is that you can have a lot of interdependencies, and at the end, this is usually called the dependency hell, el infierno de las dependencias, which is that you have a lot of problems to detect what parts, what libraries depend on which libraries, how you can remove one library. If you update one version of the library, some external library, another in whatever place stops working, this kind of thing. So be careful with the libraries. About the dependency graph, there is a metric which is CCD. I mean, the dependency graph is very easy to. The definition is that you have the vertex are the components. For example, this A is a component, and so this means, for example, that A depends on B, B depends on D, B depends on E, and so on. Okay, and there is this metric which is the CCD metric, which is cumulative component dependency, which is it measures what are the reasons to change of some module. So let's try it here. For example, module D here doesn't depend on any other module. So here the only one that the only reason to change is one. So D only has one dependency. Okay. In the case of B, B depends on D and B depends on E. So the number of this one is, as it depends on D, on E, and on itself, the number here will be 3. Okay. In the case of E, it only depends on itself. So this is 1. In the case of F, it only depends on itself, is 1 again. G is 1 again. But in the case of C, it depends on E, F, G, and on itself. So the number here will be 4. Okay. And finally, in the case of A, A depends on B, on D, on E, C, F, and G. If you count them, they are 1, 2, 3, 4, 5, 6, plus itself, so it depends on 7. Okay, so the full number, the CCD number, is the sum of all of these. So it will be 7 plus 3 plus 4 plus 1, 1, 1, 1. In this case, it's 18. Okay, do you understand how I calculated this number? So in this case, there was no circular dependency. It was this number. But imagine what happened when you add a circular dependency. If you happen, I mean, I have that in the next slide. For example, we can do it just without changing the slide. Imagine that you later say that E depends on A. And let's calculate that again. So if E depends on A, let's create again the calculus. In the case of D, this is not going to be affected. So this will remain to be 1. In the case of E, notice that now E depends on A, and A depended on all of them. So the number here will be that it will depend on all of them, which are 7. So here this number will be replaced by 7. In the case of F, it only depends on itself. So this will remain as 1. In the case of G, it only remains of itself. It remains as 1. In the case of C, it depends on E, which depended on all of them. So again, this number will be 7. In the case of B, it depends on D, but also on the rest of them. So it will remain. It will be 7, and in the case of A, it will also be 7. So now the new CCD with this circular dependency will be 7, 7, 7, 7 is 7 multiplied by 4 is 28 plus 3 is 31. Okay, so now the new number will be 31. So as you can see, if you add a circular dependency on this dependency graph, the number passes from being 18 to be 31. So this is the CCD metric, which measures what are the reasons of change of the different models of a system. So this is this calculus that I was done in the previous slide, but here with this slide. Okay. Did you understand this CCD metric? So this is a metric, as I said the other day, some quality attributes can measured with some kind of metrics. And for example, the cyclic dependencies can be measured with this CCD. And there are tools. For example, there is one tool called Structure 101, which provide you this measure, this metric. So this is why I added here to the slides. As I said before, to manage dependencies is not easy, and usually there are different models to manage those dependencies. For example, you can just install those dependencies locally. So this is probably what you did in the past in Eclipse, that you needed some jar, and you just downloaded the jar and put that in Eclipse. That's usually not a very good way to work, because later if you want to share that project with other people, you need to tell them you have to install this jar, etc. So there are other ways to automatically do that. There is also the possibility to just embed the external library in your system, but then you will have a problem with the version control, of course. So you have a problem there, or just create an external link and say, I will depend on this repository with this external link, and then I let some kind of tool to automatically obtain the jar. Okay. Again, this is not easy to do, and there are tools to automate the building. So, and now this is what we are going to tell now, is that about build automation. Build automation is usually something which is very, very important nowadays. And nowadays, I think I don't know of any project which is a bit rigorous that doesn't do any automation automatically, because if you try to do it manually, you have a lot of problems. So there are, in this part, I will talk about different tools to automate the building of the software. What are the tasks that you usually have to do? You have to compile, you have to package the software, to install some dependencies, to deploy it, etc. If you can do that automatically, then that's better. Here in the next slide, I have this. So I have some reasons, some quality attributes about why it's important to automate building. So, for example, to improve the correctness, to minimize bad builds, to eliminate repetitive and redundant tasks, to save time and money, to have some history of the builds and the releases, to improve, to be able to work with continuous integration, and also to handle this complexity. So those are some of the reasons why build automation is usually very important. And here I have this saying that I really like about, so never send a human to do a machine's job. What this means is that all the jobs that you can automate, you should automate them, because if you ask a human to do that, then those tasks will contain some errors. There will be, if they are repetitive tasks, humans will forget some of the steps and so on. So usually, I mean, this, I know that this is maybe this controversial in other domains, but when you are working with software and you are software engineers, you should try to do this. Never try to do something manually that you can do automatically, because otherwise you will create some mistakes and so on. So when to build the software automatically, when that, I mean, there is the possibility to run that on demand. So you run a script and run the software. You can schedule it, for example, in some in some systems, for example, in Apache, they had these nightly builds, or you can just trigger the building of the whole software at every commit to a version control system. And this is, for example, what we are using in the Radarin, in the lab assignment, in the skeleton of the lab assignment, is that we are trying to use continuous integration to build the whole system once you do a push to the control version system. Once you commit there, it automatically is triggered and it builds. And if you know in GitHub Actions, it will automatically compile and build the whole software, for example, the documentation, but now all the running software, it will be automatically triggered. Okay, and this is something that nowadays is the best practice, I think, is to not do that only manually when you want, but to trigger it automatically when you do a commit. But of course, if you are working locally, you can just, for example, when you say npm ram build, for example, it will automatically create the build in your machine. Okay. About build automation tools, here are a lot of build automation tools. I mean, I used, these are some of them. I think I used all of them. So in the past, when I was working with C, I was building. I was using make files. In the C world, they are still used. And I still use them for some projects, for example, for LaTeX or something like that. In Java, there was initially Ant, and later Maven is the most popular one. I have some slides now about Maven, but I'm not going to go into a lot of details about Maven, because nowadays in this year you are not using Java. I mean, you could use Java if you wanted, but you don't need to do that. This SVT is the tool that I'm using every day. I mean, not every day, but this is because I program usually in Scala. So this is the tool that I use, but I'm not going to teach you about this because the course is not about Scala. There is also Gradle in JVM languages, Rake for Ruby, and this year, for example, you are going to use npm if you are working with JavaScript. Okay, so just a very short overview. Make, this is in Linux, and Maven. This has, I mean, maybe it's quite famous because it has this configuration languages using the XML syntax. Some embedded languages, for example, some tools that have some embedded languages are this. For example, Gradle is been developed in Groovy, SVT in Scala, and so on. There are new tools for this. For example, in Google, they have this tool which is internal to Google, which is Bazel. For example, Google has only one repo for all the code that has that is the, I mean, all the project, all the software that is being run by Google is in one single repository. This is the monorepo approach. So they have a build system which allows this kind of distributed system building and all and so on. But there are other tools like Pants and Duck, but I never work with them. And now these are the slides about Maven that I will probably skip. So this is a build automation tool. This was the creator of Maven. So I'm just going to skip this part because you don't, I mean, you can take a look. And we kept the slides for reference for you. And also in the lab assignment, in the labs, you also have, I think, the same slides. So I'm skipping them. And then about npm, so this is very similar to Maven. It's similar, it's not the same. In this case, what you use as the configuration language is the file code package.json. And there's also Yarn, and there are other tools. So, and also again, I will skip this part because you can take a look later. Okay. And with this, I will end this part about building tools.